type yes in the chat box if you can hear my voice and see my screen. All right, so I am back at the office, but yeah, good morning. The internet connection is rather slow. I'm not sure why. Normally I don't have any problem at the office, but that's how things. It looks like there is probably the jinx that we have to face for 2020. Yeah, I guess this is SOP for internet traffic as well. It's rather slow. All right, but never mind. Okay, so we can continue our discussion as usual. Okay, so today we are going to continue our discussion on this frequency response analysis. We are done talking about the Nyquist diagram. If you don't really get what we were discussing, if you don't really comfortable how to compute the, for example, phase margin or gain margin and things like that, you're going to have a second chance because today we are still on this frequency response analysis, but today we are going to migrate from this Nyquist diagram. So the Nyquist diagram is the polar plot of the magnitude of the open loop transfer function and the phase angle on one single diagram. So it is called the Nyquist diagram. But there's another alternative. It is called the Bode diagram that can convey the same information. So the plot is rather different, convey the same information. So this is just alternative to the Nyquist diagram. So today we're going to talk about this Bode diagram. I know. That is not the correct pronunciation of Bode diagram. But anyway, everybody pronounced that as Bode diagram, even though we know that you're not supposed to say Bode diagram, but because everybody is saying that I'm pronounced Bode diagram as Bode diagram as well. As long as you know that what you're doing is wrong, I guess it is fine, right? Do you agree with me? As long as you know that what you're doing is wrong, but you're going to do it anyway, it's going to be fine, I guess. It is just like all those. No, I'm not going to do that. I'm going to get in trouble by saying that. Forget what do I say? Forget about what I have been saying. All right, so today we are going to, so the correct pronunciation of this Bode diagram is in fact you're supposed to pronounce this as Bode diagram. It is Bode diagram. Okay, but since everybody is pronounced as Bode diagram, there's no problem. I have no qualm about it. All right, so let us continue. See. It says that Bode diagram is an alternative to the Nyquist diagram. It is just an alternative. It will convey the same type of information as the Nyquist diagram. So the Nyquist diagram is a polar plot of the frequency response function of the open loop transfer function GH of J omega as a with frequency as parameter, while the Bode diagram is the plot of the gain, the same magnitude of the transfer function in decibel. You need to convert the magnitude of the open loop transfer function into decibel. Decibel is just a ratio with respect to a reference point. You do not take the absolute value of the magnitude. You take the decibel of that. The decibel is just 20 log of the gain. So that's the definition of decibel. And then you plot that versus frequency. And then on another plot, you plot phase angle versus frequency. So you're going to have two to plot instead of a single plot as in the Nyquist diagram. In Nyquist diagram, you have a single plot. You have the magnitude and angle in a polar plot. So in the Bode diagram, we have this horizontal and vertical axis. You're going to have two plots. One plot for the magnitude versus frequency, and the other is the phase angle versus frequency on the same scale. But since our omega is from 0 to infinity, and then sometimes our magnitude is going to be very, very small, so we're going to take the log scale on the horizontal axis. And then we're going to use the linear scale on the vertical axis. It is called the semi-log graph paper. I'm not sure whether you're familiar with semi-log graph paper or not, but you can go to the internet and see how the semi-log paper looks like. See, this is how the semi-log graph paper looks like. It is a log scale on the horizontal axis. Let me find the, okay, here, it is a good one. What the hell is this? All right, so here, this is a good one. So you have a log scale on the horizontal axis, and you have this linear scale on the vertical axis. So this is called the semi-log graph paper. Since our frequency is from 0 to infinity, so if we use a linear scale on the horizontal axis, then it's going to take a long way before we can reach infinity. But if we use the log scale, and then you say 0.1, and then you go to 1, and then you go to 10, and then you go to 100, 1,000, 10,000. So you're going to reach infinity very quickly. So this is just an example of semi-log graph paper. So we are going to draw our Bode diagram on this semi-log graph paper. Okay, so let's done with that. So it is just the same information. So let's go to my notes. Okay, I have double checked. You on your e-learning, you have this note on your e-learning. I just uploaded this. So this is notes 12-1. So Bode diagram. This is Bode diagram. So Bode diagram conveys the same frequency response information as the Nyquist diagram. It is a plot of the magnitude of the open loop transfer function in decibel versus omega on one plot, and then there's a second plot. You have this phase angle versus frequency omega. So you're going to have two plots. Okay, so the horizontal axis is omega with a log scale, and then the linear scale in the vertical axis. But this is in a unit of dB. You must convert the magnitude of the magnitude of the open loop transfer function to decibel, and then you plot that on a semi-log graph paper. The same thing here. You plot the phase angle versus frequency. Since the frequency is from 0 to infinity, so if you use linear scale on the horizontal axis, then of course you're going to go around the world before you can reach infinity. So this is now, I'm not sure whether you have used semi-log papers or not before, but if you haven't done today is the day that you use your first semi-log graph paper. So this is now, you have two plots instead of just one, the magnitude versus omega and the phase angle versus omega, and that's it. So now you have your Bode diagram instead of the Nyquist diagram. You can still know whether the system is stable or not. You can still read the value of gain margin and phase margin from the Bode diagram. Okay, so now here, this is decibel. The unit must be in decibel. So the definition of decibel here is, this is the definition of decibel. It is just 20 log the magnitude of the open loop transfer function, or 20 log of anything. It is called that just a decibel. For example, the noise level is measured in decibel. Decibel meaning that the measurement is with reference to a reference point, not at the absolute value. But anyway, so it is just the definition of decibel is 20 log whatever the value of your gain, of your magnitude, and log here is log of base 10, not the natural logarithm. This is just the normal log base 10. Okay, with that definition, now you are ready to draw the phase diagram. No, you are ready to draw the Bode diagram. So how do we interpret whether this, once you have drawn the Bode diagram, how do we interpret whether the system is stable or not? How do we get the gain and phase margin from a stable system? Okay, so for a stable system, the curve of the decibel crosses the frequency axis. Frequency axis is the horizontal axis to the left of phase over frequency. Okay, so phase over frequency is when the phase angle is equal to 180. So look here. Okay, so this is your Bode diagram. Once you draw the Bode diagram, you're going to have this curve. This red line is the curve that you're going to get. Okay, so you plot decibel versus frequency, and then you're going to plot this phase angle versus frequency. And then when the value of phase angle is 180, so the frequency at that, the frequency correspond to the phase angle negative 180. So that is by definition is called the phase crossover frequency. So this is a phase crossover frequency. Phase crossover frequency is the frequency when the phase angle is 180. So what is the gain crossover frequency? If you still remember correctly, the gain crossover frequency is when the magnitude is equal to 1. When the magnitude of GH of S is equal to 1. So when the magnitude is equal to 1, 20 log 1, you're going to get 0. So the decibel for 1, you are going to get 0. 20 log 1. So when your magnitude is 1, the decibel is going to be equal to 0. Okay, so log 1 is just 0, multiplied by 20 is still 0. So the gain crossover frequency is when your decibel is equal to 0. So this frequency is, by definition, is the gain crossover frequency. So the frequency when the phase angle is 180 is known as the phase crossover frequency. So how do you know whether the system is stable or not? The system is stable when the curve of the decibel crosses the frequency axis. Frequency axis is the horizontal axis to the left of phase crossover frequency. So this is now an example of a stable system. So this is the phase crossover frequency, and then the curve of the decibel crosses the horizontal axis to the left of phase crossover frequency. Then we know that this is now a stable system. The point where the decibel curve crosses the frequency axis is known as the gain crossover frequency. Okay, so the phase crossover frequency is when phase angle is equal to 180. Okay, for a stable system, you can now determine the gain margin and the phase margin. So you can read directly from the Bode diagram. So the gain margin is positive downward. You read the gain margin at the phase crossover frequency. Again, here the gain margin is going to be in unit of decibel instead of the normal 1 over x. You can always convert to the gain margin when we talk about gain margin in Nyquist diagram. The gain margin in Nyquist diagram is not in a unit of decibel. It is 1 over x. X is the absolute value of the magnitude of the open loop transfer function. But here, the gain margin is going to be in unit of decibel. You can always convert that to the absolute value of gain margin in terms of just the 1 over the magnitude. And the phase margin is read here, is measured from negative 180 is gamma. So this is a phase margin. It's measured from the negative 180 positive upward. We measure that positive upward. So the gain margin is measured positive downward. So whatever you get, so you get whatever value that you read, the gain margin is positive for a stable system. All right. So the gain and phase margin can also be computed the same way as the computation for Nyquist diagram. So here, for those of you who are still not clear how to compute the gain and phase margin, we are going to go through again the same way that we have computed the gain and phase margin for Nyquist diagram. Okay, so that is my explanation for the book diagram. Okay, so this is book diagram. Okay, there's not much there. Okay, there's nothing much there. We will come back to this example for 11, for 12. We'll come back to this for 13. Okay, okay, that's it. Let's take a look at my example. All right, so I'm going to jump straight away to example 419. There's not much discussion because both diagram is just convey the same information as the Nyquist diagram. So we are going to jump to example 419. Don't worry about it. We will come back to this later. Example 411, for whatever. But today we are going to go straight ahead to 419. Why is that? You might want to ask. Why do I jump straight away to 419? Okay, why do I do this? Why do we jump straight ahead to 419? Because your memory about the Nyquist diagram is still fresh. It is just yesterday that we talk about the Nyquist diagram. We talk about how we can compute the gain margin and the phase margin from the Nyquist diagram. So if we waited until maybe next week, you probably have forgotten all about it. This is the perfect time for us to jump to this example 419. Okay. For a system shown below, draw the book diagram for k is equal to 1. So there's a reason why you want to draw a book diagram or Nyquist diagram for k is equal to 1, because your gain margin is going to tell you how big the value of controller gain k that you can have before the system become unstable. See, when you draw the book diagram for k is equal to 1, your gain margin, the absolute value of your gain margin, tell you straight away, right away, the maximum value of the gain k that you can have before the system become unstable. So there's a reason why we always draw our Nyquist diagram or book diagram for k is equal to 1. That's one of the reasons. So from the book diagram, obtain the phase margin, obtain the gain and phase margin. Estimate the critical value k for stability. So this is just the same question. This just as easily be a question in your test. The same problem. It says for the system shown below, draw the Nyquist diagram. Everything else is the same. But now you just change the word Nyquist to both diagram. Everything else is just the same. So draw the Nyquist diagram for k is equal to 1, determine the phase margin and gain margin, estimate the critical value k for stability, and now all you do here is just change the name Nyquist to book diagram. So that is why I jump straight ahead to this 419, because your memory is still fresh. So when you want to draw the Nyquist diagram, you get the open loop transfer function. That's it. Okay, so the first thing that you need to do, okay. All right, so here, determine the gain and phase margin, and I add something here, design the value of K such that the phase margin is 30 degrees, and determine the corresponding gain margin. So I add a little bit more requirement to the question here. So I want you to design what is the value of K such that the phase margin is equal to 30 degrees. There is just the normal extension. So this is just the normal extension of the question in your exam. So you're going to earn another 4 marks answering this extension. So drawing the board diagram, determine the gain and phase margin, you'll get 6 marks. Normally you will get 6 marks. Answering the extension of the problem, which is designing the value of K for a given value of gain of phase margin, you'll get another 4 marks. That's it. Okay. So now this is your system here, your closed loop control system. So now for K is equal to 1. For K is equal to 1, then you need to obtain the open loop transfer function. So that is just your open loop transfer function. 5 multiplied by K, but K is equal to 1. And then you have your numerator. Is this the same problem? Is this the freaking same problem? What the hell is this? Yeah. No, doctor. It looks like the same problem. Oh, never mind. The same problem or not the same problem, who cares, right? As long as now we are talking about the boot diagram. All right. So now this is now your open loop transfer function. So now substitute S with J omega, and then you will get this expression is going to be in the form of complex number. A complex number will have the magnitude as well as the phase angle. Okay, so this is your magnitude. 5. The magnitude of 5 is just 5. The magnitude of pure imaginary number is just that. The magnitude of that imaginary number on its own. But now here you have this imaginary part and the real part as well. So that is the magnitude of the second term. That's the magnitude of the third term. It's the same thing that we have done for the Nyquist diagram. And then the phase angle. The phase angle for 5 is 0. The phase angle for 1 over S is -90, and so on and so on. But here you need to have this another thing here, decibel. Decibel is just 20 log of that magnitude. And so you're going to have another column in your table. Right? So now you can, again, the selection of frequency is the same way that we have selected range of frequency for Nyquist diagram. Remember that we are going to look for frequency 0 to infinity. So we need to select appropriate value for frequency so that the distribution of our point is going to be well distributed on the graph paper. So now, okay, it is the same. It is the same. Probably not. I don't know. It looks the same. Probably not. It's the same problem, but never mind. I just know. Probably different. All right, anyway. So when you draw the Nyquist diagram, you need to determine the range of frequency. The range of frequency. So 1 over T max is going to give you the minimum frequency. 1 over T minimum is going to give you maximum frequency. So this is the 2 points that you need to look at. And then you add a few more points. So here I add another frequency equal to 1, frequency is equal to 50. And then you compute this magnitude and phase angle the same way you compute the magnitude and phase angle for Nyquist diagram. So the second column here for the magnitude, you compute that using this expression, the same way that we have been computed the magnitude for the Nyquist diagram. And the last column here, the phase angle, you compute this using the same expression as you have computed for the Nyquist diagram. Only now you have this additional column, this decibel column. Decibel column is just 20 log of this magnitude. So if you have your calculator ready, you can double check. So 20 log 4.89 here is going to be 13.8. And for example, 20 log 0.2 is negative 13.98. So you might want to double check this conversion from absolute value of the magnitude to the decibel. Okay, hopefully that I have done that correctly. So now you have your extra column here in decibel. So when you want to draw the boat diagram, all you have to do is plot this decibel versus frequency, and then you plot this phase angle versus frequency. But of course, frequency must be, the axis for frequency must be on a log scale. Okay, so let us now transfer all this point into our semi-log graph. Okay. Again, there's some reminder here. Note that the time constant are 0.2 and 0.5. So the range of frequency is selected around 1 over T1 and 1 over T2, the same way that we have selected frequency for the Nyquist diagram. And then with the value of this extra column here, we can now ready to draw the boat diagram. Okay, so now we are ready to draw the boat diagram using the semi-log scale. Okay, so the first plot is, of course, the decibel versus frequency. The decibel versus frequency. Now, the vertical scale is a linear scale. Look at, so the value is now here 0, 20 decibel, negative 20 decibel, and negative 40 decibel. So this is the vertical axis. Linear scale for vertical axis. 0, so now that's 20. If you go another, you go 40. So if you go below 0, that's negative 20. So there's negative 40. On the horizontal axis, you have the log scale. So starting here at 0.1, so 0.1 is exactly at the origin here. And 1, and you go 1 decade is 10, and you go another decade is 100. You go another decade is 1000. It is not linear. Again, the value of frequency at the vertical axis is not 0. In this case, it is just 0.1. If you go another decade, that's 0.01. You're never going to reach 0 on this log scale. So the horizontal axis here, you're never, no matter how far you go to the left, you are not going to reach 0. 0 here is the value of decibel, the value of your vertical axis. The value of frequency there is 0.1. And 1 decade later is 1, and 1 decade later is 10, 1 decade later is 100. Let me go back to this log, semi-log paper. Why can't this is having problem with this? Okay, so here, look here. On the horizontal axis. Okay, so there is 0.001. There is 0.01, there's 0.1, there's 1, there's 10, there's 100. And look at the vertical line. Vertical line are not equally spaced. So if this is 1, if you go, this is 2. 2 is far away from 1. And then the line is going to get closer and closer and closer. So there's 1, there is 2, there is 3, there is 4, there is 5. So the value of 5 is already 2/3. It's not exactly in the middle. So the scale on the horizontal axis is not linear. You need to be aware of that. Okay, so now we are ready to transfer our point. Okay, so the first point is 13.8 decibel frequency of 1. 13.8 frequency of 1. So that is frequency is equal to 1. So that is your 13.8. So that's 20 decibel. Halfway is 10 decibel. So 13 or 14 is more than 1/2 of this scale. Frequency 1, decibel 14. And your second point, frequency is 5 at -3 decibel. Frequency is 5. So 5 is not exactly halfway between 1 and 10. No. 5 is not halfway between 1 and 10. This is a non-linear scale. 5 is about 2/3 between 1 and 10. So that's 5. So this is 5. And then the value of decibel is -3. Okay, so you go on. The third frequency is 10. So decibel is -14. So you go to 10. So this is -14. And then 20. 20 is about 1/3 from 10 at 27 decibel. So this is 20. This is 20. 20 it is about 1/3 from 10. So there's 20, and then you go down 27 decibel, and finally at 50, frequency equal 50. So the value of decibel is 48 decibel something again. So this is 50 decibel. 50 decibel is not halfway between 10 and 100. So you must go a little bit further. And so that is your final point. Now you join those points together and you will get the decibel curve, or the first diagram of your book diagram. Okay, so that is how you transfer the point of this decibel versus frequency. And next you have to transfer all this phase angle versus frequency. So again you get 1, 2, 3, 4, 5 points. Okay, now you transfer for phase angle. Phase angle start at 0, -90s. You need to rescale properly your vertical axis. So -90, -180. This is a rather odd scaling. Normally we put 100, 200, 250, 300 like that. But for some reason I prefer to put -90, -180, -270 like that. And then you can now transfer all your 5 points, 1, 2, 3, 4, 5. So frequency is equal to 1, 104, -104 degrees. So this is frequency 1, frequency 100, frequency 10, frequency 100. So this is your 5 points. You can double check whether that point is accurate or not. You might want to get 1 or 2 semi-log graph paper and print it so that you can draw your book diagram quite accurately. So it's 1, 2, 3, 4, 5 points. Join those 5 points together, then you get the curve for your phase angle. So that is how you draw your book diagram from this table. I'm not going to discuss today how we can get the gain margin and phase margin and whatnot. So that's the end of discussion today. Just how to transfer all these points to a semi-log graph paper. So a boat diagram, you're going to have two diagrams. One is the magnitude versus frequency, and the other is the phase angle versus frequency. So the magnitude is in unit of decibel. Okay, so do you have any question? All right, so if you don't have any questions, so that's the end of discussion today. I guess I'll see you next year, I guess. So yeah, so our next class is next year. See you next year, everybody.